Hi everybody. I wanted to look at a rectangular solid with you. My third try this morning. I'm going to get it right this time. I'm going to show this rectangular solid. I declare it to be 9 by 12 by 20. It could be inches. Now I'm going to get the length of a main diagonal in a moment. First though, I'm going to get a length of a face diagonal. That'd be pretty easy to do. I could have found the length of this diagonal. That's one of the face diagonals right there. And that was going to come up pretty cleanly. I would recognize there's a right angle here. This face is just a rectangle. And if I wanted that diagonal, I'm going to call it X for the moment. I could hit it with the Pythagorean theorem, and you might know the answer already. 9 squared plus 12 squared ought to equal X squared. That's the hypotenuse that X is. So I got 81 plus 144 is equal to X squared. Those add up to 225 is equal to X squared. And when you take the square root of both sides, X would have been 15. Why I said you might know it already is because that's just a 3, 4, 5 triangle. 3 times 3, 4 times 3, and 5 times 3. That's just using a Pythagorean triple. And if I wanted to get a main diagonal now, there's a couple ways you could go. A main diagonal would go from this vertex to this one. And I think I could use that main diagonal as the hypotenuse of a right triangle that contains that length of 15. I'll try to show that triangle carefully and kind of shade it up for you so you can find it really easily and get a good look at it. Let me take a second and do that. Is there a right angle in this fella? And actually we should recognize that if this line is perpendicular to this plane, then it's perpendicular to every line in that plane that passes through its foot. So yeah, this line should be perpendicular to that diagonal and to these other segments as well. And since this length was 20, and this is a rectangle solid, this length would have also been 20. And if I use these numbers, the 15 and the 20, I ought to be able to get the length of that main diagonal. I'll go with 15 squared plus 20 squared is equal to, I'll call it MD for just the moment, squared. And I get 225 plus 400 is equal to the main diagonal squared. Those add up to 625 equals the main diagonal squared. And when I take the square root of both sides, the main diagonal is the square root of 625, which I declare to be 25. So that would have worked here. But I think there's a quicker trick for doing that. Something that you could use that you won't have to go through so much drawing these triangles and working so much through. You can get the length of a main diagonal this way. This is worth writing down and keeping in your notes. It is given by the square root of the length squared plus the width squared plus the height squared. You just square them all up, add them, and take the square root. Let's see that it works on this guy. That was a 9 by 12 by 20. That would imply that I'd give it 9 squared plus 12 squared plus 20 squared. You're going to see it's really going to recapitulate these very same numbers. 9 squared gets me 81. 12 squared gets me 144. And that 20 squared gets me 400. Adding those up, and here I get 225, just like we did when that should have been an 81, shouldn't it? I'm sorry. Just like when we added those up before, we got 225. Plus, you're going to put that 225 with that 400, and this is going to all add up to, hit it with your calculator, 625. And I know the square root of 625 is just 25. So this is a pretty clever way to get the length of the main diagonal. But you had one in your homework with a rectangular solid whose lengths were, let me remember what they were. On your rectangular solid, they were 6 by 8 by 24 on a homework assignment just recently. The homework assignment titled, Work Out with the Pythagorean Theorem in a Few Solid Figures. Your rectangular solid was 6 by 8 by 24. And if you would have used this axiom, you would have got the proper length. That would have been 6 squared plus 8 squared plus 24 squared. And you would have said that's 36 plus 64 plus 576. These two add up to 100 plus that 576, so I got 676. Alexa, What's the square root of 676?
The square root of 676 is 26.
So, the length of the main diagonal you should have had in that homework assignment on the Pythagorean theorem with a few solids. The main diagonal should have been 26. Using this confirms that idea. I want to show you a couple of other things too, please. On that same assignment, you had to work with this square base pyramid. All the base edges were 10, 10 by 10 by 10, and the lateral edges were all 13. We just went over this in class. I don't want you to have the same opportunity that we have in class. One of the things you had to find the length of was a slant height from the vertex to the midpoint of a base edge. I'm going to show that slant height and find its length. It comes up pretty quick. I'm going to call it VM, reminding myself that M is really a midpoint of that segment right there. A simple thing to do is to pull that triangle off and get a good look at it. This triangle VBC. The base edge is 10. These sides are 13 and 13. I think you might already know that length, but let me just go through those motions with you. I'm going to show that slant height VM. I know that in an isosceles triangle, the altitude would bisect the base, and that thing is a perpendicular. So this would be 5 and 5 out of that 10 all across the bottom. And hit that with the Pythagorean theorem, I'm going to get what's called the slant height. VM squared plus 5 squared ought to equal 13 squared. And that gives me VM squared plus 25 is equal to 169. Subtract 25 from both sides, and I got VM squared is equal to 144. Take a square root of both sides, and I'm agreeing with you that, get that right, VM should be 12. That's what this length would have been, and that's what this length must be on this square base pyramid. But then it gets to this place where you got to find the length of the altitude. And that number's so ugly, I just thought I would go back over it with you. Let me show the altitude Vx to the center of the base, and show this segment so I can get a right triangle going that has Vx as one of its legs. We do know the length of that hypotenuse, it's 12. What about the length of this lower edge here? And I hope you're thinking if this distance all across here is 10, from midpoint to midpoint would have also been 10, so midpoint to the center of the base would have been 5. That length has to be a 5 right there. And now I can hit it with the Pythagorean theorem and I'll be able to get Vx. Let me shade that triangle I'm looking at because it may be kind of hard to find it, figure out what I'm talking about. A right triangle there, and 5 squared plus Vx squared would equal 12 squared. And we get 25 plus Vx squared is equal to 144. Subtract 25 from both sides and we get Vx squared to equal 119. Take the square root of both sides, and that's the length of that altitude. It's an ugly number, the square root of 119. I don't think there's much I can do with it. It's not that terrible a number. The square root of 121 would be 11, and this is just a little less than 11, so it's about 10.9, I figure. But I want to show you another way you could have done that, if you bear with me. Since we know about 45, 45, 90 triangles now, take a look here. Just going to do a little adaptation of work on this thing. Could you have known the distance from this vertex to the center? And I think you could. And that would give us a chance to use the Pythagorean theorem. Let me shade another triangle that has that as one of its legs, and still find that length of that altitude again. I know it's still going to be the square root of 119, but I just want to work with it. Could we know that length there? I know that the lateral edges were all 13, so this length would have been 13. Now what about this distance from that vertex to the center of the base? So take a look at this square. If it was truly 10 by 10, all the way around, what would be the distance from that vertex to the center of the base? That length, I say, is the same as that length right there. And because you now know about 45, 45, 90 triangles, you would probably think, well, if I wanted to know that full diagonal across there, this would have been a 45, 45, 90, because it's an isosceles right triangle. The full diagonal would have been 10 square roots of 2. Just knowing about 45, 45, 90. So what about this part? From the center to one corner would have been 5 times the square root of 2. And that would have been another 5 times the square root of 2 there. So, going back to this place, and that length has to be 5 times the square root of 2. And this isn't terribly important, but it is something you probably want to recognize. Now, can I get that altitude Vx? I know it's supposed to be this dreadful number, but could I confirm that dreadful number? And I think I could. Working on this right triangle this time. With this leg, I'm trying to find that leg Vx, and I know the hypotenuse is 13. So 5 square roots of 2 squared plus Vx squared ought to give me 13 squared, using the Pythagorean theorem. Hey, how do you square this number? Well, I got to square that 5, which will give me a 25. I got to square the square root of 2, which gives me a plain old 2. So this is really 25 times 2. We'll call it 50. Plus Vx squared is equal to 169. Subtract 50 from both sides. I got Vx squared is equal to 119. And we take the square root of both sides, and we're back to that square root of 119. So there's just not a better answer than that one. But at least I've confirmed it, and I know that it is true. You also had some of these to work with. And they are really a pretty ridiculous question. But let me just walk you through this, since you got to deal with a couple of them. Special right triangles, extra for experts, and thinking you might be an expert. And I built a 45, 45, 90 here, with a 45 and a 90, and adjacent to that I got a 30, 60, 90, and here's another 45, 45, 90, and here's another 60, must be a 30, 60, 90 there. And we're going to find the lengths of all these sides and figure out the perimeter of the figure. Let's get started down that path. This triangle got a 45 and a 90, must be a 45, 45, 90. The things that I'm going to remember when I walk through this page, a couple special right triangles that I should memorize when you have a 45, 45, 90. What are the simplest numbers that would fit on this triangle? It'd have to be 1, 1, and the square root of 2. And if you had a 30, 60, 90 triangle, I'm trying to think about the most simple numbers that could fit on this 30, 60, 90 triangle. Let that be 30, this one be 60. Hope you know those numbers already. Ought to be 1, 2, and the square root of 3. We should memorize these two triangles, absolutely. And we can predict any length on any 45, 45, 90, or 30, 60, 90 by knowing about these. How these work, that's how these will work. In this 45, 45, 90, it's got to be isosceles. So this is 6. This would have also been 6. And that hypotenuse would have been 6 times the square root of 2. And I'm done with that triangle. I'm going to move into this next one then. That's 6 square roots of 2. If there's a 30, that must be the 60 up there. That must be the longer leg. I got to go from the longer leg to the shorter leg in this 30, 60, 90 triangle. How do you go from the longer leg to the shorter leg in a 30, 60, 90 triangle? I got to divide by the square root of 3. So I'll take the length 6 square roots of 2 and divide it by the square root of 3. Got to rationalize that denominator. Don't want to leave a radical in the denominator. It's not good form. So I'll multiply by the square root of 3 over the square root of 3. And what would that give me? Multiplying straight across the top, we got 6 square roots of 6 over, and the square root of 3 times the square root of 3 is a plain old 3. So we really got 2 square roots of 6, huh? That would have been the short side of this triangle. 2 square roots of 6. Now, I'm in this 30, 60, 90 triangle. I think I got to realize, where am I? Where do I want to go, and how do I get there from here? I'm at the short side, opposite the 30. I wish I knew the hypotenuse of that triangle. To go from the short side to the hypotenuse, you double the short side. So I should double this length to get that hypotenuse. It would be 4 root 6. And then I got to think, well, what kind of triangle are you working in now? I think I'm done with that one. I'm going to work with this next triangle, and it has a 45 and a 90. In fact, it's a 45, 45, 90. So it is isosceles. If this length was 4 root 6, then this length would have been 4 root 6. Now I've got to figure out the hypotenuse of that triangle. I ask myself, generally, how do you go to the hypotenuse in a 45, 45, 90 if you already know the legs? And I say you got to multiply by the square root of 2. So I should take that number, 4 square roots of 6, and multiply it by the square root of 2. I'll do that right now. Kind of cute stuff happens with it. That says 4 square roots of 6, and I'm going to multiply by the square root of 2, and that gives me 4 square roots of 12. maybe I can work on that, because I do know something about 12. 12 is 4 times 3. I know the square root of 4, which is going to be 2. So that 4 comes out, becomes a 2, multiplies with that 4, it gives me 8 square roots of 3. And that's what that hypotenuse would have been. Yep, 8 square roots of 3. All I had to do was multiply by the square root of 2, but it cleans up to be a different looking number, doesn't it? 8 square roots of 3, I needed to write right there. Be careful. Okay, now, done with that triangle as best I could. I'm going to look into this 30, 60, 90 triangle. It's got a 60 here and a 90 there. Must be a 30 up there. And what side do we know of that 30, 60, 90 triangle? I know the hypotenuse, huh? Well, how do you go from the hypotenuse to the short side in a 30, 60, 90 triangle? Well, you divide it by 2. So I should divide this by 2, and it'd just be 4 square roots of 3. Now, if I could just get that longer leg opposite the 60. So I asked myself, how do you go from the short side to the longer leg in a 30, 60, 90 triangle? You multiply by the square root of 3. That's just 1 times the square root of 3 right there. So I got to multiply this number times the square root of 3. I'll take a second and do just that. 4 square roots of 3 times the square root of 3 gives me 4 square roots of 9. But the square root of 9 is just 3, so this is 4 times 3, so it's just 12. I declare that that length has to be 12. Now, I've done as much as I want to do there. I got to find the perimeter on this figure. And there's some things that I can add and some things that I can't. If this were 6 and this were 6 and this were 12, I can add those up and that'd be 24, huh? Plus, I got these square roots of 3 hanging over here, but I got nobody that plays with them. Nobody in their same league. I'll just keep that 4 square roots of 3. I'm not going to add any of these inner segments, just the outside edges as I do the perimeter. What about these two fellas? Could we sum those together? Yes, we could. That would be 6 square roots of 6. Without belaboring things, I mean, I could work this other one. We're going to work a couple of them in class, but I don't want to make this video too darn long. So I'd say there's a good look at playing around with 30, 60, 90s and 45, 45, 90s. So have fun with your assignment, guys. Thank you very much.